Hi guys, and welcome to the next lesson on metallic bonding. Today, as underlined, you can see the learning outcome is Unit 1, Area of Study 1B, dot point 1. We're looking at the the nature of metallic bonding and the structure of metallic crystals. We've covered the common properties of metals: luster, malleability, ductility, heat, and electrical conductivity. And now we're going to be talking about how atoms of metals bond together and the structure of metallic crystals, and how this gives the properties, this explains the properties of metals. So the properties of metals were discussed: ductility, conductors of heat, electricity, lustrous, and reactivity by losing electrons, as well as high melting and boiling points. And this reflects the atomic structure of metals. So from the information, all of these properties, it's clear that metals consist of charged particles that can conduct electricity. They have strong forces of attraction between their atoms, which explains why they have high melting and boiling points, because you need a lot of energy to break apart the bonds, therefore a high melting and boiling point. But some electrons can be easily removed. That gives explanation of why they react with each other, why they form charges, and why some of them are very reactive, like sodium in water, potassium in water, etc. So metals, this is a structure of a metal here. Metals are constructed of positively charged ions, we know as cations. So from a metal cation is a positively charged ion there. And you have a delocalized, meaning it's localized in this area. It's not surrounding that one atom. Sea of electrons. So you have lots of different cations of the same element. So for example, these could all be sodium here. Sodium atoms that have lost an electron. All sodium atoms. And then the electrons that they've lost are actually moving or swimming in a sea or delocalized sea of electrons. So metals have a number of properties, and they're based on their chemical structure. Scientists have come up with a model. Now, a model is a way of explaining something that's been refined over time to explain why metals bond and give their properties. So I've already talked about the made of positively charged cations here, metal ions, surrounded by lots of delocalized negative electrons. The electrons are delocalized or spread through a large area, and they're strongly attracted to the cations. So they can't just fly off, they can't move away out of the lattice or out of the structure. They are bonded by electrostatic or positive and negative charges. So positive and negative will attract each other. And that's what causes them to come together, stay together. So in this GIF here, you can see that the electrons in the red, here and here and here, the electrons in the red are moving around the cations, or the positively charged ions. They can't swim away, but they can move throughout that structure there. Another diagram showing you that electrons can move, just remove that text there, electrons can move throughout the lattice here, but they cannot disappear or they cannot move away entirely. So that sort of gives an idea that when you see electrons moving, that's how electrical current is conducted. That suggests why they can conduct electricity so well and why they conduct thermal heat so well too. So this is just another image showing you how metals are made up of positively charged metal cations and negatively charged electrons in the sea of electrons, or delocalized sea of electrons. Positively charged cations are closely packed together, and that's called a lattice. Their structure, when they pack together, that's a lattice, LATTICE. When the negatively charged electrons are arranged, they're free moving, as we've already spoken about, through that lattice, and that free moving structure is based on the outer shell electron. So the valence electrons will break off and they'll move into the sea of electrons, whereas the inner shell electrons remain within the atom. So there's your positive ions there, and there's your electrons there, the negative. And this is the lattice, so here's the plane. The electrons are in the red, electrons in red, and then the ions, metal ions, in blue. So the properties of metals and how they're explained by their atomic structure. So this table here comes from the textbook, Chemistry 1 textbook, and it's sort of an explanation or a nice summary of why the metallic bonding gives it its properties. So metals are hard and they have relative high boiling points. So if you look at the positive charge and the negative charge, remember how I said positive and negative attract? So that's called an electrostatic attraction, electrostatic forces. The electrostatic attraction between the positive and the delocalized electrons or negative, they hold the lattice together. That makes them quite hard, makes them hard to break. You can't snap a nail in half very easily, a thick nail in half, whereas you can snap something much easier like a pencil in half. Metals are good conductors of electricity. As I already mentioned, the electrons are moving freely throughout the lattice. As you can see here in blue, the electrons, or here in red, the electrons, they're moving freely. They're moving from a negative to a positive electrode. They can be conducted in that way. Therefore, they can conduct electricity to make a circuit. If you look at a battery, you've got a negative and a positive end. All it is electrons moving from the negative end to the positive end. That's how you conduct electricity. Since metals already have that, a lot of metals do conduct electricity quite well. Metals are malleable and ductile. So malleable means they can bend without breaking. And ductile is being able to draw it into a wire. So when the metal is bent, the electrostatic forces allow them to slide past each other and they hold them together. So the delocalized electrons enable the attraction between the positive ions, but they enable them also to slide alongst each other so they can be bent without being broken easily. So for example, you bend a piece of glass, it'll shatter. It won't be able to, it's not very malleable. You bend a piece of metal, it can bend and it'll hold its structure. If you keep bending it, it will break, but if you bend it a couple of times, it will be okay. So the limitations of the model. This model is not perfect. Now, the metallic bonding theory explains many properties of metals, but some cannot be explained. So, for example, why are there a range of melting points? If sodium has a +1 electron and potassium has a +1 electron, why are there a range of melting points between the two of them? Shouldn't they be the same if they both have one outer shell electron? Hardness, so the ability to scratch other objects. Their densities, why are some metals more dense than others, but they have the same number of valence electrons? Why do they have different conductivity as different metals? Again, same number of valence electrons, or their bonding is the same in terms of the ratio of cations to negative electrons. And the magnetic nature. So cobalt, iron, and nickel are magnetic. What's special about their electron configuration or their model of the bonding of the atom, of the metallic bonding, sorry, that makes them conductive or magnetic? Why is mercury or osmium, why is it a liquid at room temperature? All of these things can't be explained by the model. So there are things to consider. It's not perfect, doesn't account for everything, but that's what a model is typically. It's the best representation of the understanding of how metals work. This is a summary of today. Metallic bonding refers to the bonds between metal atoms. Metallic bonding involves cations, positively charged ions, and a sea of delocalized electrons. It's arranged in what's called a lattice. Metallic bonding is responsible for a number of key properties observed in the metals, and the metallic bonding is not perfect, and the model has limitations. These are the questions to complete 1 to 3 of chapter review on page 62 of Chemistry 1 textbook.